In this video, we are going to be looking at how to find the domain of an algebraic function. So we're going to look at several examples throughout this video. We're going to look at about 8 examples, and you'll notice that in the examples, they all look kind of similar. They have the same things showing up in them, but we're approaching the different problems in different ways, depending on whether we have denominators or whether we have square roots or cube roots or things like that. So let's get started with our first example. We want to find the domain of this function. Now this function has a denominator. And when we're finding the domain of a function with a denominator, we have to make sure that the denominator does not equal 0. Because we're never allowed to divide by 0. It's perfectly fine to have 0 in the top of the fraction, but it is not okay to have 0 in the bottom of the fraction. So whatever is in the bottom of the fraction, we set that not equal to 0. Now we're going to solve this equation. This is a quadratic equation, and I'm going to solve it by factoring. You could also use the quadratic formula to solve this equation, but I'm going to choose to solve by factoring, and I'm also going to use grouping to solve it. So I'm going to group the 3 and the -4 to give me a -12. And now I'm looking for two numbers that multiply to -12 but add up to -11. And the two numbers that do that are -12 and +1. So I'm going to use the -12 and the +1 to rewrite that -11x. So I still have 3x squared, but I'm going to replace the -11x with a -12x and a +1x, because those were two numbers that added up to -11, so we haven't changed the problem. And then I'll still keep the -4 and have that not equal to 0. And now that I have expanded it into 4 terms, I'm going to start grouping. I'm going to group the first 2 terms together, and I'm going to group the second 2 terms together. In the first 2 terms, they have a 3x in common that I can pull out. That's going to leave us with an x minus 4 on the inside of the parentheses when we pull out the GCF of the first 2 terms. And then in the second 2 terms, I'm not going to factor anything out. It's already an x minus 4, and so I'm just going to leave it as an x minus 4. And I'm leaving that one as an x minus 4 because I want these 2 pieces to have that common factor of x minus 4. But then I'll pull that out and be left with 3x from the green piece plus 1 from the red piece. Don't forget about that 1. Sometimes people forget about that 1 there, but think about if you were to distribute that x minus 4 back out to the 3x, then you would get all of this. But if you distribute the x minus 4 back out to the 1, that's how you get the x minus 4 that we had to start with. So now that we have done all of this work to have it factored, I'm going to take each of the factors, the factor of x minus 4, and set it not equal to 0, and the factor of 3x plus 1 and set it not equal to 0. So solving the first equation, I'll add 4 to both sides to get that x cannot be equal to 4. And then solving the second equation, we'll subtract 1 and then divide by 3. To get that x cannot be equal to a -1/3. So those are the 2 numbers that x is not allowed to be. Sometimes it'll be okay depending on your teacher or whatever's grading your assignment. If you're doing it online or taking a test or something like that, you can write all real numbers except for those 2 numbers, because those are the 2 numbers that make the denominator equal to 0. So those are the numbers that we would want to exclude from the domain, -1/3 and 4. And if you were writing the domain in interval notation, then I would start with a number line just to help you form the interval. I'd put -1/3 on the number line, and I'd put 4 on the number line. And I put both of them with open circles because it's like they're being cut out of the number line. They're being excluded. But everything else, everything to the left of the -1/3, everything in between the -1/3 and the 4, and everything off to the right of the 4, that is okay. That's included in the domain. So I'm just going to erase this so I have a little bit more space to write the interval. So now that I have that number line formed, I could write the domain in interval notation. This number line starts all the way off at negative infinity and goes up to negative 1/3, the yellow piece of shading. And then it skips over negative 1/3. So I'm going to use that U symbol to union it with negative 1/3 and 4. And then I'm going to use another union symbol to glue it to the last piece that starts at 4 and goes off to positive infinity. So this answer here that I'm boxing in now, that is the domain in interval notation. So depending on how you're asked to write it, you can write it in either one of those two ways. Just real quick, I'll show you one more way that you could see it written. And I won't write it in all three of these ways for all of the examples, but another way you could write it is the set of x such that x cannot be negative 1/3 and 4. That's in set notation. So it just depends on how you have to write it. So that's our first example. Now let's go look at our second example. Our second example has the same expression showing up, that quadratic of 3x squared minus 11x minus 4. But in this example here, it's not in the denominator. There's nothing else going on in the function besides just that quadratic. And when we're finding the domain of algebraic functions, the only two things we worry about are denominators or even radicals or even roots. And we'll see an example of that in a second. But this doesn't have either one of them. And don't get confused and say that this too is an even root or an even radical. It's not. That is an even exponent. And even exponents don't give us a problem. So the domain of this function would be all real numbers. This has no domain issues. There's nothing that we need to restrict because it wasn't in the denominator here. So you could write that as an interval as negative infinity all the way to positive infinity. Everything on the number line works. Let's look at the next example. So here we have a function g of x is equal to the square root of 5 minus x. This function does not have a denominator, but it does have an even radical. That square root, there's an understood 2 on the outside of it that we don't write. So what the problem with even radicals is that you can never take an even radical of a negative number. That's not possible. So for instance, you can't tell me two numbers that multiply to negative 16 and they are the same number. Because if it was a positive 4, that would give you a positive 16. But if it were a negative 4, that would also give you a positive 16. So sometimes, if you've learned a little bit about imaginary numbers, that's technically an imaginary number because it's not real. And we don't have that problem for odd radicals of even numbers. And I'll explain that when we get to that example, but it's because neither one of these came out to be negative 16 that we have to make sure that whatever is under the even radical cannot be negative. Whatever is under the even radical cannot be negative. That's why that was a problem. So if it can't be negative, then it can either be positive or it can be 0. So it can either be greater than 0 or it can be equal to 0. So I've taken what was under that even radical and I set it greater than or equal to 0. And now I'm going to solve this equation. So a couple ways you can move things around here. I will subtract 5 from both sides first to get that negative x is greater than or equal to negative 5. And then I want to solve for x, so I'm going to either multiply or divide both sides of the equation by negative 1. Same difference. But when you multiply or divide in an inequality, the sign changes direction. So make sure that from here to here, the sign flips because you're dividing by a negative number. So I get that x is less than or equal to 5. I could write this in set notation, the set of x such that x is less than or equal to 5. I could say all real numbers that are less than or equal to 5. I can make a number line, and on that number line I'll put 5 with a closed circle because it is okay for x to be equal to 5. This does have the or equal to. We can take 0 under even radicals. And because x is less than 5, I'm going to shade to the left of it. My shading starts at negative infinity, and the infinities always get parentheses. and the shading goes up to a +5, which is included, so it gets a bracket. And that would be the domain in interval notation. So now let's look at the next example, which is very similar to the last one, but the only difference in this example is that it's a cube root instead of a square root, because it has that little index of a 3 on it right there. So when we're finding the domain of something with a cube root, we don't have the problem that we have with even radicals. Because for example, if I put -8 under a cube root, that has an answer that's not imaginary. That answer is -2, because what number do I multiply by itself 3 times to get -8? That's -2. -2 times -2 times -2 is -8. So I can use an odd number of blanks, an odd root, and still get a negative number. So that's not a problem. So if that's not a problem, then the domain of this function is all real numbers. I don't have to make sure that whatever is under that radical is greater than or equal to 0. Because it's okay for it to be less than 0. It's okay for it to be negative. So that's the difference between even radicals and odd radicals when finding the domain. Now let's look at this example here. We have a fraction. We've seen before in our first example that the issue with fractions is that we have to make sure that the denominator does not equal 0. So I want to make sure that this square root of 5 minus x is not 0, but it's also a square root. And remember, the things with square roots is we make sure that what's under the square root, like what we did here with the 5 minus x, we made sure that what was under the square root was greater than or equal to 0. So typically I would take what's under this square root of 5 minus x and set it greater than or equal to 0. But because it is also in the denominator, I don't want it to equal 0. Because denominators cannot equal 0. It's not okay for us to divide by 0. So I'm going to erase this or equal to. That comes off. I just want to set it greater than 0 because it was in the denominator. If it wasn't in the denominator, we could keep the or equal to on it. But because it's in the denominator, we have to make sure that it doesn't equal 0. And we've already solved this inequality before. I'll solve it again really quickly. To get the x's less than 5. This time I don't have the or equal to on it because we didn't have that. So if I were making a number line for this case, I would put an open circle on 5 because the open circle means that it is excluded. And I will shade to the left and have my interval from -infinity to 5 as the domain in interval notation. So that's how you treat even radicals that show up in the denominator. Now sometimes a lot of the questions that I'll get will be, well, you didn't do anything with the numerator. You don't have to do anything with the numerator unless there's an even radical in the numerator. Numerators don't give us problems. Numerators are allowed to be 0. We don't have to worry about them the way that we have to worry about the denominator. The only time that we'll deal with the numerator is if there is an even radical in the numerator. So this had no even radical in that numerator, so I'm just going to ignore it. In our next example, it's the same thing starting off. This numerator has no even radical in it. I'm going to ignore that one. The only thing I have to worry about is I have to worry about the denominator, because we can never have the denominator be 0. So I'm going to take the denominator and I'm going to set it not equal to 0. Now notice that in this example, I don't have to worry about the whole greater than or equal to 0 thing and then erase the or equal to. It's not like the last example, because this square root here, that was an even radical. The square root has a little 2 out there, that's an even radical. This is an odd radical, so it doesn't matter about what's happening under it. I just have to make sure that the whole thing doesn't equal 0 to make that entire fraction 0. So to solve this equation, I'm going to cube both sides, because cubing both sides will get rid of that cube root, and it will leave me with negative x plus 5 cannot be equal to 0, because 0 cubed is 0. And then I'll add x to both sides of the equation. I'll just flip both sides that I'm writing this on to get that x cannot be 5. So 5 is the only number that would make the denominator be equal to 0. And so 5 is the only number that I need to exclude from the domain. This would be all real numbers except 5. So I'm shading everything else on the number line that starts at negative infinity and ends at positive infinity to see that my domain in interval notation is negative infinity to 5 and then 5 to infinity. So both of the 5s have parentheses because parentheses mean that it's excluded. It's being cut out of the domain. Here we have another example. This example is a lot like this one, but the difference is that the numerator and denominator are flipped. So let's see how we're going to deal with this. In this example, we cannot ignore this numerator because this numerator has an even radical in it. And you can't ignore even radicals, because what the thing with even radicals is whatever is under them, this negative x plus 5 cannot be negative. It has to be greater than or equal to 0. That's what we have to worry about with even radicals. And I can keep the or equal to here because that even radical was not in the denominator. So I didn't have to worry about that. But this function also has a denominator, and I have to make sure that the denominator does not equal 0. Now we've already solved both this equation and that inequality. We solved this equation back in this first example here. This is the exact same equation. We get that x cannot equal negative 1/3 and 4. So I'm just going to go ahead and jot that down here. X cannot equal negative 1/3 and x cannot equal 4. We've also already solved this inequality. We get that x is less than or equal to 5. Remember, the sign flips when we divide by that negative 1. So we have 3 pieces of information here. Less than or equal to 5, but cannot be negative 1/3 and cannot be 4. So I'm going to put all 3 of those pieces of information on the same number line. So I'm putting an open circle on negative 1/3 because x cannot be equal to that. I'm going to put an open circle on 4 because x cannot be equal to 4. Those two numbers have open circles because they're excluded. And then I'll put a closed circle on 5. Because 5 is included in that inequality because it was underlined, less than or equal to 5. So because this was less than or equal to 5, I can only shade the numbers that are smaller than 5. But I can't shade 4 because x can't be 4, and I can't shade negative 1/3 because x can't be negative 1/3. But I can shade everything to the left of 5. I can't shade anything to the right of 5 because x has to be less than or equal to 5. So now we're ready to write the domain. In interval notation, we're writing what red parts of the line are covered. Anything with open circles gets parentheses, meaning it was not included, and anything with closed circles gets a bracket. And you have to jump over open circles because that's not included. So this is an example where we have a denominator that we have to make sure the denominator is not 0, and we also had an even radical in the top, and we had to make sure that it was not becoming negative. The last example that we're going to look at is very similar to the first example that we looked at. So here was the first example right here. And the difference between this example and the new example that we're going to look at is that I've switched the numerator and the denominator. And I want to look at this example because sometimes people think that just because a function has a denominator that it means there's going to be domain problems, and that's not always the case. So what we have been doing with our denominators is we have been setting them not equal to 0. But if I take this denominator and I set it not equal to 0, then I have 3 is not equal to 0. And that's something that's true. There's no x value here for me to solve for. I don't have to go find the x value that's going to make this true. That's always true. This denominator is never going to equal 0, no matter what x is. So when I draw the number line for the domain of this function, there's no numbers that I have to put open circles on. There's no numbers that I have to exclude from the domain. So the domain of this function is all real numbers, from negative infinity to positive infinity. So just because a function has a denominator does not mean that it's going to have domain issues. It depends on whether or not there is an x or a variable that shows up in the denominator. If all you have in the denominator is just a number, that's not going to give you any domain issues because that number is not going to be equal to 0. Well, I hope you have found this video helpful. I wanted to look at lots of different types of examples that went along with finding domains so you can see the different things that happen in different situations. If this video was helpful, please do give it a thumbs up. And if you haven't already, subscribe to my channel. I'll see y'all next time. Bye.